The first Tesla ever made was powered by laptop batteries. Not metaphorically. Not inspired by laptop batteries. Literally the same cylindrical cells sitting inside the laptops of that era. Just 6,831 of them, wired together under the floor of a sports car. Nobody had ever done anything like it. Nobody knew if it would even work. That was 2008. And it worked. Since then, the battery inside an electric vehicle has become one of the most fought over, most rapidly changing, and most misunderstood pieces of technology on the planet. Right now, in 2026, the global EV battery market is worth roughly $95 billion. By 2034, analysts expect it to hit $435 billion. That is not a niche industry. That is the backbone of the entire automotive future. But here is what most people miss. EV battery is not one thing. It is at least 6 different chemistries, 3 physical shapes, and 2 charging voltage architectures. And every choice changes what the car can do, how safe it is, how long it lasts, and what it costs. We are going through all of it, every chemistry, every cell shape, why some cars charge in 18 minutes and others take all night, and the supply chain problem every automaker is quietly trying to solve. Let's start with the chemistry, because that is the heart of it. All current EV batteries are lithium-based. The chemistry that defines each battery, what its electrodes are made of, is called cathode chemistry. Change the cathode material and you change the energy density, cycle life, safety, cost, and the supply chain required to build it. The first chemistry worth knowing is NMC. That stands for nickel manganese cobalt, and it is what most Western EVs run today. BMW, Volkswagen, Hyundai, Kia. If you are driving a non-Tesla EV in America, there is a good chance it has NMC chemistry inside. The reason is energy density. NMC can store between 150 and 220 watt-hours per kilogram of battery weight, which means more range for a lighter pack. That matters a lot when you are trying to get 300 miles out of a mid-size SUV. NMC comes in variants. NMC 811 pushes nickel to 80% for more density, but that makes the cell more thermally sensitive. More energy in, more heat to manage. The problem with NMC, and with almost every high-energy EV battery chemistry right now, is cobalt. We will come back to that, because it is a bigger issue than most people realize. NCA, nickel cobalt aluminum, is what powered the original Tesla Model S and Model X. Up to 260 watt-hours per kilogram, the highest density of any commercial chemistry. The trade-off was thermal sensitivity. NCA cells need precise management and do not tolerate abuse. Tesla has largely moved on from it. Now here is the chemistry that is quietly winning, even though it should not be the obvious choice on paper. LFP, lithium iron phosphate. On the surface, LFP looks worse. Its energy density is only 90 to 160 watt-hours per kilogram, noticeably lower than NMC. For the same range, you need a heavier battery. Not great for a vehicle already carrying extra weight compared to a gas car, but here is what changes the story. LFP lasts far longer. Where an NMC battery might survive 500 to 2,000 charge cycles before dropping to 80% capacity, an LFP battery regularly hits 2,000 to 4,000 cycles. Some CATL cells are rated to 12,000 cycles. Charge your car every single day, and that could mean 2 or 3 times the usable life from the same battery. LFP also runs safer. The temperature at which an LFP cell enters thermal runaway, the dangerous chain reaction that can cause a battery fire, is around 518 degrees Fahrenheit. NMC cells hit that threshold closer to 392 degrees Fahrenheit. That 126-degree gap is enormous from a safety engineering standpoint. LFP also carries no cobalt and no nickel, which makes it cheaper to build and far less tied to risky supply chains. BYD runs LFP in every vehicle it makes. Tesla uses it in the standard range Model 3 and the Powerwall. As of 2024, LFP accounts for 56% of all new EV battery production in China, passing NMC. The supposedly inferior chemistry is now the market leader. Real-world durability and cost beat peak specs on a datasheet. BYD pushed LFP one step further with their Blade battery. The cells are ultra-thin prismatic rectangles, each one 38 inches long, longer than a baseball bat. They slot into the battery pack like blades in a rack, with no separate module housing around them. Less material overhead, more space for actual cells, more energy in the same physical volume. Now there are two more chemistries worth knowing, because they are shaping what comes next. NCMA is what GM built its Ultium platform around, the technology behind the Chevy Equinox EV, Silverado EV, Blazer EV, and the Cadillac Lyriq. NCMA adds aluminum to the standard NMC formula, which cuts cobalt content by roughly 90% compared to early NMC chemistry, while actually improving thermal stability. A bridge chemistry, better ethics, lower cost, still competitive range. Then there is LMR, lithium manganese rich. GM is targeting 2028 vehicles. It swaps most cobalt for manganese, which is far cheaper and more geopolitically stable. Energy density lands between LFP and NMC. If the production yields hold, it could become the next dominant chemistry in American EVs. Here is the supply chain story nobody tells at the car dealership. Cobalt. 73% of the world's supply comes from a single country, the Democratic Republic of Congo. The DRC has confirmed child labor in its artisanal mining operations. Multiple tech companies have faced lawsuits over this. Cobalt prices swung from $82,000 per metric ton in 2022 down to $25,000 in 2024, partly because battery makers were running away from it as fast as chemistry allowed. LFP winning market share in China is actually geopolitically significant. Less cobalt needed means less dependency on a single unstable supply chain. The whole industry is moving in this direction as fast as the chemistry allows. Now let's talk about what the batteries look like physically, because the shape of a cell matters just as much as what is inside it. Three main form factors exist in EV batteries: cylindrical, prismatic, and pouch. Cylindrical cells. The original Tesla Roadster used the 18650 format, 18 mm in diameter, 65 mm long, the same cell in laptops and power tools at the time. Tesla moved to the 21700 for the Model 3 and Model Y, slightly larger, 20 to 30% more energy per cell. And then in 2022, Tesla introduced the 4680, 46 mm wide, 80 mm tall, 5 times the energy of a 2170 cell, 6 times the power output. Those are not incremental improvements. That is a different category. The 4680 also introduced a tabless design. Current collects across the entire face of the electrode rather than through narrow metal tabs. Internal resistance drops, charging speed goes up, heat under load goes down. The most striking thing about the 4680 is how Tesla deploys it in the Cybertruck. The floor of the Cybertruck is the battery. Cells bond into a flat structure replacing what would be a separate chassis floor. No chassis rails under the pack. The pack is the structure. Weight saved, rigidity gained. Prismatic cells are flat, rigid rectangles, usually enclosed in an aluminum case. BYD's Blade battery is a prismatic cell. CAT-L and Samsung SDI use prismatic formats across many of their products. The advantage is packing efficiency. Flat cells stack cleanly with no wasted space between them, unlike round cylinders, which always leave gaps. Pouch cells skip the hard case entirely. Sealed in a flexible, foil-like aluminum polymer bag. No wasted material on housing, highest volumetric efficiency of any form factor, meaning they pack the most energy into a given volume. GM's Ultium packs use pouch cells, so do many Hyundai and Kia batteries. The downside is that pouch cells can swell when overcharged or damaged, and without a rigid housing, that swelling can become a structural problem inside the pack. Let's move to charging, because this is where battery design connects directly to the experience of owning an EV. 2-voltage architectures exist in production cars today: 400-volt systems and 800-volt systems. Most EVs on the road run 400 volts. That includes every Tesla, most Chevys, most Fords. It supports DC fast charging at up to 250 kilowatts, which the Tesla Supercharger V3 delivers as much power in 15 minutes as a standard 120-volt home outlet delivers in 5 full days. But 800-volt systems are faster. The Porsche Taycan was the first in 2019. Since then, the Hyundai Ioniq 5, Kia EV6, and Lucid Air have followed. The physics: power equals voltage times current. Double the voltage, double the power at the same current. Less cable heat, less connector stress, faster charging. The Ioniq 5 hits 10 to 80% in 18 minutes at a 350 kilowatt charger. Home charging is level 1, 120 volt, 3 to 5 miles per hour, or level 2, 240 volt, full charge in 4 to 10 hours. Most EV owners install level 2 in their garage and never need anything faster. One more thing on charging: battery preconditioning. Cold temperatures slow lithium-ion chemistry significantly. Most modern EVs now warm the battery automatically while you drive toward a fast charger, so you arrive ready for peak speed. Without it, you plug in and wait. Sounds minor. In real-world charging time, it is not. Thermal management more broadly is one of the places where EV design really separates good from bad. The original Nissan Leaf used air cooling, just ambient airflow moving through the battery. Cheaper and simpler, also one of the biggest product failures in EV history. Leaf owners in Phoenix, Arizona, where summer temperatures regularly exceed 110 degrees Fahrenheit, watched their battery capacity drop dramatically. Some lost more than 40% of their original range. Air cooling cannot keep up when you are managing a large lithium pack in a hot climate. Tesla runs liquid cooling with glycol loops through the pack, integrating battery, cabin HVAC, and motor heat into one system. In winter, waste heat from the motors warms the battery. GM and Hyundai now treat liquid thermal management as a baseline requirement, not a premium feature. Now let's look at where batteries are heading, because two technologies are about to change the conversation. Solid-state batteries swap the liquid electrolyte for a solid material: ceramic, glass, or polymer. Liquid electrolytes are flammable. Solid ones are not. Energy density could reach 400 to 500 watt-hours per kilogram, versus 200 to 300 for the best cells available today. Toyota is targeting a 2027 to 2028 commercial launch, with up to 745 miles of range per charge. Most analysts think 2030 is more realistic. The engineering challenge is not making a solid-state cell that works in a lab. It is making one that survives hundreds of real-world charge cycles. Electrode materials expand and contract slightly each time. That stress opens microscopic cracks in the solid electrolyte. Nobody has solved this at scale yet. The second technology is sodium-ion, and this one is actually shipping now. Sodium-ion batteries swap lithium for sodium. Sodium is the other half of table salt, roughly 1,000 times more abundant than lithium. No lithium, no cobalt. Raw materials essentially everywhere. KTL entered mass production of their sodium-ion battery, called the Naxtra, in 2025. Energy density sits between 120 and 160 watt-hours per kilogram, approaching LFP territory. It also outperforms LFP in extreme cold. At -4 degrees Fahrenheit, sodium-ion cells hold their capacity better than lithium iron phosphate. If KTL scales this successfully, it breaks the geopolitical dependency on lithium mining almost entirely. KTL at 37% and BYD at 17% are both Chinese companies, together controlling over half of global EV battery production. That concentration is driving Western governments and automakers to build domestic supply chains as fast as they can. Here is the honest summary of where things stand. NMC gives you the best range per pound right now, but it depends on cobalt. LFP gives up some range but lasts significantly longer, costs less, and runs safer. And it is winning market share because of it. Solid state is the next potential step change, but the manufacturing challenges are real and the timeline is uncertain. Sodium-ion just entered production and could cut the lithium dependency entirely if the economics hold. The battery in your future EV will be cheaper, lighter, safer, and longer lasting than anything on the road today. The chemistry is moving fast. The infrastructure, mines, factories, charging networks, is not. That gap is where most of the friction in the EV transition actually lives. So here is the question worth sitting with. If sodium-ion batteries hit the same energy density as today's NMC at half the raw material cost, and there is a real path toward that, what happens to lithium prices? What happens to cobalt? What happens to the entire mining supply chain the current EV industry is built on? Drop your answer in the comments. Seriously, I want to know what you think breaks first. Solid state finally crosses the finish line, or sodium-ion makes lithium irrelevant. If this helped something click that was confusing before, hit the like button and share it with someone who keeps asking you what the deal is with EV batteries. Subscribe. Next video, we are getting into how EV motors actually work, and there is one detail about how they generate torque that makes combustion engines look like they were designed blindfolded.